So most people, from fairly early on in their math career, they learn to graph things using what are called rectangular coordinates. So that's the x comma y, so far over, so far up, right? Um, Very standard Cartesian coordinate system. Well, there are other ways of doing this, right? There are other ways of locating a point in a plane. What we're going to talk about now, that we can talk about now that we have our trigonometry functions, is something called a polar coordinate system. And the way this works, right, instead of being over a certain amount and up a certain amount, what we're going to do instead is we're going to go over and around, right? So instead of doing two distances, an x and a y, like we do with our very traditional rectangular system, instead we're going to specify a point using a distance r and an angle theta. All right, so let's look at some examples. All right, so first all I want to do right now, I want to just see how we can take these polar coordinates and turn them into actual points on this piece of polar graph paper here. So 6 comma pi over 3. Okay, the first distance, this is the radius, right? That's r. So I'm going to go out 6 units from the center. There's some names here. The center is called the pole. That's what would be the origin in our Cartesian system. And there's only one axis here. Right? There's only one axis. It's this line here going out to the right from the pole, and it also has a name. It's called the polar axis. All right, so what I'm going to do to find my point here, I'm going to go 6 units out. Right, so that's going to be 1, 2, 3, 4, 5, 6. So that's right here. And then I'm going to go pi over 3 units around. Okay. You could make that 60 degrees if that's easier for you to work with, right? You can always go back to degrees. But notice kind of the slightly darker lines here, right? This one is pi over 6. This one is 2 pi over 6, which is pi over 3. This one is 3 pi over 6, which is pi over 2, and so on around the circle. So we actually can get kind of our standard radian measure angles really pretty quickly. So I'm going to start at this point here, and I'm going to go around to pi over 3, and that's where this point is. This is the point 6 comma pi over 3. Okay, so how about 4 comma 0? Well, that's a distance of 4 and an angle of 0. So I'm going to go out 1, 2, 3, 4 units. And an angle of 0, right? So an angle of 0, I'm going to stay right there on the polar axis. So this is 4 comma 0. And my last one here, right, I got one more 5 comma pi over 2. 5, that's 1 unit further out, so that would be here. Then I'm going to go around pi over 2 radians. Well, that's 90 degrees. So that's going to be right here. So that point will be 5 comma pi over 2. Okay, good. So those are some basic points, right? Well, there are a couple of interesting things for us still to talk about. So I've got a few more points here. Let me clear out the ones we just did so we can kind of have a clean slate to work with. You see the first one there, what do we do if we have a negative radius? Okay, well, you notice how when I counted out my distance, I started at the pole and went to the right? Okay, well, A negative radius value just means go backwards. All right, so first I'm going to do the angle. I'm going to do pi over 3. That's this line here, right? And instead of going this way like I would with a positive radius, I'm going to go the other way. I'm going to count 1, 2, 3, 4, 5, and 6. And there is the point -6, comma, pi over 3. Okay, so let's see, how about the next one? 4, comma, pi over 2. Well, that one's actually pretty standard. I'm going to go out 1, 2, 3, 4, and around pi over 2. So that's 4, comma, pi over 2. Now, I picked that one on purpose, right? Let's take a look at the next one. -4, 3 pi over 2. Okay, 3 pi over 2. That's and I know if you have to, it's 270 degrees. So that's this line here. But instead of going here in the positive direction, I'm going to go the other way. I'm going to go the other way 4 units. So it's going to be 1, 2, 3, 4. And look at what happened. I landed on that exact same spot. So this point 4, comma, pi over 2 and -4, comma, 3 pi over 2 are the same point. Right? There's two different ways of writing the same point. So this is one of the kind of unusual things about this polar coordinate system. Unlike in the Cartesian system that you're used to, there's more than one way to specify the location of a given point. Right? In other words, the coordinates of a given point aren't unique. All right, so just kind of keep that in the back of your mind as we're going along here. So the next thing that we want to be able to do is we want to be able to convert back and forth between these two systems. So in other words, if I give you a polar point, if I give you a point r, comma, theta, I want you to come up with the equivalent x and y values. Right, well, let's see how we can do this. I'm going to pick a point r, comma, theta, right, and just some arbitrary point here, right, something out here. So what do I know? I know that this distance is r, and this angle is theta. And what I want to know is, what are the x and y coordinates? What is this distance and this distance? Well, if I put a triangle in here, right? If I drop this line down here and add a right triangle to the mix, now I can use our old school right triangle based definitions. I know that, let's see, I'm going to do the x first. So I know that x over r is the cosine of theta. And I know that y over r is the sine of theta. Remember, I wanted x and y, right? So multiply both of these by r, and I get x equals r cosine theta, and y equals r sine theta. And those are my formulas. Right? That's it. Those are the formulas I'm going to use to go from a polar point to a rectangular point. All right, so let's look at a couple of examples here. Let me write my formulas just so we have them to reference. X equals r cosine theta, and y equals r sine theta. So let's see. Let's put numbers in. Right, this first one, r is 2, and theta is pi over 3. So that means x is 2 cosine pi over 3. And y is r sine pi over 3. Let's see, cosine pi over 3, that's a half. So this is 2 times a half, which is 1. Right? And over here, sine of pi over 3, this is going to be 2 times the square root of 3 over 2, which is the square root of 3. So there's my answer. This polar point is equivalent to the rectangular point 1, comma, square root of 3. Okay, so how about this one? We actually looked at this one before. I know already that this point is on the polar axis, which is the positive x-axis. So let's see what happens. Hopefully that's what I come up with here. X is 4 cosine 0. Y is 4 sine 0. Cosine of 0 is 1, so that's just 4. Sine of 0 is 0. So yeah, my point is actually came out the same, didn't it? In this one unusual case, right? Don't count on that happening very often, right? But the point is on the x-axis, which is the positive x-axis, which is exactly what we expected. Okay, so now next one, this is another one where we kind of know where it is. Pi over 2 is 90 degrees, so this point should be on the y-axis. Well, let's try it out. X equals 3 cosine pi over 2. Y equals 3 sine pi over 2. Cosine of pi over 2, that's 0. Sine of pi over 2 is 1, so this is 3. And yeah, the point 0, 3 is on the y-axis. Excellent. Just exactly like we expected to happen. Okay, so how about going the other way? Right, now I know x and y, and I want to turn this into r and theta. All right, so let's just kind of walk through the same process here. I'm going to pick a point out here, and this point is x, comma, y. So, what do I know? I know that this distance over is x, and this distance up is y. And what do I want to know? I want to know what is this distance r, and what is this angle theta. Well, again, I'm going to kind of take the same approach. I'm going to drop a line down here and make a right triangle, and then I can use this to get what I need. First, to get r, I'm just going to use the Pythagorean theorem. R squared equals x squared plus y squared, which means r is the square root of x squared plus y squared. And now how about theta? Well, look, I know that the tangent of theta equals y over x. And then let's take the inverse tangent. Inverse tangent of both sides. Theta equals the inverse tangent of y over x. And that's my formula. It's not an ideal formula, right? Because remember when, especially if you're going to your calculator, you ask it for the inverse tangent of a number, it's always going to give you that something that's in that inverse tangent's range. It's going to give you a number between negative pi over 2 and pi over 2. In other words, you will always get a first or fourth quadrant angle. So what if your point is in the second quadrant? Then what do you do? Well, you may have to adjust, right? You may have to adjust and add pi, for example, to move the angle around to another angle that has the same tangent, but that's in the quadrant where we need it to be. All right, so let's look at some examples. We'll see how this works. So I've got some points here, right, for us to look at, and let's see what happens. I'm going to use my formula, my two formulas. So let me write those up here. R equals the square root of x squared plus y squared, and theta equals the inverse tangent of y over x. Okay, so to take my first point, 4, 4, r is the square root of 4 squared plus 4 squared. That's the square root of 32, which is 4 times the square root of 2. Okay, good. Theta is the inverse tangent of 4 over 4, which is 1, right? So this one I know. I know that the angle whose tangent is pi over 4 in the first quadrant, because that's where my point is pi over 4. So there's my point, 4 square root of 2, comma, pi over 4. Okay, so let's try the next one. Right, I'm going to do r first. R is the square root of negative 5 squared plus 12 squared. That's the square root of 169, which is 13. Okay, so far so good. Now, theta is the inverse tangent of 12 over negative 5. And for this one, I'm going to go to my calculator. Right, my calculator says this is negative 1.176. We're still doing radians. Okay, but is that actually my angle? Well, no, it really isn't. If you think about where that point is, negative 5, comma 12 is over here somewhere. Right, it's in the second quadrant. And that is a first quadrant angle. Okay, so how can I fix this? All you have to do to fix this is remember that the period of the tangent is pi. So if I add pi to this, I know I'm going to get an angle that has the same tangent, right? Because that's how the period works. Well, my calculator tells me that this is 1.966, and that, convert it to degrees if you have to, but that is a second quadrant angle. It's between pi over 2. Pi over 2 is half of 3.1. It's 1.5 something. It's in that neighborhood. And pi is 3.14. 1.966 is between those two. So yeah, that is a second quadrant angle, which is what I needed. So that my point is, right, to answer the question, 13, comma 1.966. Okay, so one more. You can try this one if you like. You can pause this and see what you can come up with. Okay, so let's see. R is the square root of negative 3 squared plus negative 4 squared, which is the square root of 25. That's 5. All right, so then theta is the inverse tangent of y over x. That's the inverse tangent of negative 4 over negative 3, which my calculator says is 0.927. Okay, not what I needed. That's the first quadrant angle, and negative 3, negative 4 is over here someplace in the third quadrant. Okay, so I could fix this. I could fix this the same way I did before. Or I could just add pi to it. Or you get 4.069, right? And that'll work. Another way you can fix this, right, is to say, look, if I tried to graph this point, it would be over 5 around 0.927. It's up here somewhere, right? I want the same point, but in the other direction. Right? I want this point over here. So another way we can fix this is just by making the r value negative, right? So if I said negative 5, comma 0.927, that works, right? That describes the point that I'm looking for as well. And you can check these, right? Use the r, x equals r cosine theta, y equals r sine theta formula. Convert it back into rectangular coordinates, right? You can use that to confirm that you really did get the right location. Okay, so that's the basics, right? We know how to plot polar points, polar coordinates, and we know how to convert back and forth between polar and rectangular coordinates, both directions. All right, so what are we going to do next? Well, next we're going to take a look at some equations involving polar coordinates and see how we can switch back and forth between polar equations and rectangular equations.